Hey mathletes. Okay, here we go. Last video we talked about infinite sequences. In this one, we're going to talk about an infinite series. And what does that mean? Well, all a series is we're just finding the sum of a sequence. So we better know sequences before we do series, right? Now, in Math 31, the only type of series and sequence we really look at are geometric. Okay, there's definitely way more types that you'll see in higher mathematics, but for us, just geometric. And an infinite series is a series that would continue forever. So how could we possibly find the sum of a sequence that continues forever? Well, let's look at the same two sequences from the last lesson. Remember what I left you with was I said, I can find the limit of this first one because the sequence is getting smaller. And I cannot find the limit of the second one because the sequence is getting larger. How do I know? Well, I can look at these and tell they're getting bigger and smaller, but in a series, what we want to talk about is the ratio. So the ratio, to find the ratio, you take any term, so little r for ratio, you take any term and divide it by the previous one. So a quarter divided by a half is a quarter multiplied by 2 over 1, which is a half. The ratio is a half. Because the ratio is smaller than 1, I know this is getting smaller. On the next one, if I didn't recognize the ratio, I take any term and divide it by the previous one. The ratio is 2. That means it's bigger than 1. That means as I'm multiplying, the sequence is getting larger. Okay, now I know some of you are like, listen, I could tell you the ratio is a half and 2 just by looking at it. But on more complicated functions or sequences, I should say, you're definitely going to need to do this little rule. So the ratio is any term Tn divided by the previous term, Tn minus 1. That's a handy little thing to know. When the ratio is smaller than 1, that means it's going towards a value that we can find, a limit. This tells me I'm convergent. And when my ratio is bigger than 1, I'm moving away from a single number. I'm going to call that divergent. Just like that, my friends. So the first thing we want to analyze is, what is our ratio? When a series is divergent, it means we cannot determine the sum because it's growing without bound. There's nothing for us to do. When a series is convergent, meaning it's moving towards a limit, an actual value, we can determine the sum. And our formula for that is this. Sum, S, sigma, actually the Greek letter, and it is T1 over 1 minus R. And some people call T1 A, right? Alpha. Again, the Greeks, right? Alpha means first. Either way you want to think of it, there it is. So the sum of an infinite series is the first term divided by 1 minus the ratio. That easy. So let's go back up. So this first one here is convergent, so we can find the sum of it. So I say the sum, as I go to infinity, of T1 over 1 minus R. Well, my first term was, what was it, a half? A half. And my ratio also happened to be a half. My apologies, I'm going to have to go sideways here. That's bad math, but I'm out of room. So guess what? That's 1/2 divided by a half. That's simply just going to be 1. Okay? So when you're finding the sum of an infinite sequence, The sum, if you even just add the first 3 or 4 terms together, so that's what I'm going to do here really quickly. If you add the first 3 or 4 terms together, this is already 0.875. That's pretty close to 1. We're not far off already. The sum will approach, the first 3 or 4 terms will approach the actual sum because it's getting smaller so fast. So the first 3 or 4 or 5 terms will make up the largest portion of the infinite series. So that's an easy way to kind of check your work. Add the first few terms up, see what you get. It should be relatively close to what you told me it should be. Okay, not a complicated thing. Now, something that's a little new that you haven't seen so far, something known as sigma notation. So sigma is the Greek letter S, so sum, right? We're going to add these things together. So this guy here is sigma, right? That's the Greek letter right there, sigma. And what you have here, just change pen colors, is a counter. So it starts when n is 1. So that's where I start. And the top is where I end. So I'm going to go to infinity. And this is my function. So here's how this goes. It's a really slick way to write a series. So what it's telling you is let n be 1. So I let n be 1. That's my first term. There's my first term. I let n be 1. Plus, I then count up on my counter. So I let n be 2. And I let n be 3. All the way down to ... n is infinitai. Something like that. Okay, so that's how sigma notation works. Okay, how do we use it? Well, the easiest thing for us to do is to actually figure out these first few terms. Okay, so the first term then would be exponent of 0. So that would just be 3 times 1, which is 3. Okay, the next one would be 3 times a half. The next one would be 3 times a quarter, right? You're already picking up on the pattern, right? 3 times an eighth plus ... Now, I'm just going to simplify that. That's 3 plus 3 halves plus 3 quarters plus 3 eighths. Like you're really seeing the pattern at this point. So when we've got sigma notation, figure out your first few terms. Then you can figure out your ratio. So your ratio is any term, 3 halves, divided by the previous term. And again, I'm out of room here, so I'm just going to have to squeeze it in. So times 1/3, which is a half. That's your ratio. Now, some of you might have recognized that right off the bat, right there. That's your ratio in a geometric sequence. But if you didn't recognize it, you write the whole thing out. So now that I know that the ratio is smaller than 1, and when I say that, when I say the ratio is smaller than 1, I should be really, really specific here. The absolute value of r is less than 1, which means my ratio is between -1 and 1, because we can have a ratio of -1 as well. Ratios that are negative. So what's the sum of this bad boy? T1, well, term 1 is 3, over 1 minus r, which is 3 over a half, which is 6. So when you've got sigma notation, find the first few terms, find your ratio. If it's convergent, you can find this series. Okay, one last question, and we are done. For what values of x is the following series convergent? Okay, so it's geometric. It has to be. So I'm noticing my ratio is I'm multiplying each time by 5 plus x. But for what values is this thing convergent? So remember what I kind of alluded to in just a moment ago. My absolute value of my ratio has to be less than 1. The other way to say that is my ratio has to be between negative 1 and 1. Okay, so here's what I know. I know my ratio. So what I'm going to do is I'm going to sub my ratio into this inequality, just like that. And now I'm just going to solve. Really what I've got from here is I've got two parts. I've got this part, and I've got this part. Okay, I'm just going to isolate for x. Okay, so on this one, I'm going to subtract over the 5. So what do I have? I've got when x is greater than negative 6. And then on this one, I'm going to subtract 5. So I've got when x is less than negative 4. So this series is convergent for when x is greater than negative 6 or when x is less than negative 4. Okay, so that's it. Those are your values for when this thing is convergent. Hope that helps, my friends. I will see you another time.